Hi cohort, I thought I would post a video trying to kind of recap what I think we were doing in Quant on Sunday because it was kind of a lot of material, and I just thought in case you wanted to be able to go over it one more time, I would post a video. I'd like to first of all talk about the handout that Sheldon gave with some examples, and then I'd like to show you an example from my own practice to show you how one might actually want to do this kind of analysis in our own work. I'm not sure I'll be able to make it under the 10-minute YouTube time limit, so I might have to break this up in 2 videos. Okay, but anyway, this is one of the examples of linear regression that Sheldon did on Sunday. So the first step in linear regression is to pick 2 variables. So in this case, we have months of tenure and salary. So months of tenure is here on our x-axis, see right down here, and your current salary is on our y-axis. And the first step in regression is to make a graph to see if we even suspect that there's a relationship. When I look at this graph, there's no way I expect there's a relationship. I don't see any kind of linear trend. I just see kind of blobby, scattery dots. So in the real world, we would stop right there. We would say, no, there's no relationship between these two. There's no reason to expect there was. But just for the sake of going on and going over the handouts, we'll keep on going. But in any event, the first step is to look at a picture. And the picture will tell you whether you expect there's a relationship or not. Based on this picture, I really don't expect there is one. Okay, so let's take a look at what else is provided here. So the other thing that's provided here is correlations. Let's take a look at our next page. Okay, so these are the 3 important charts, and what we want to be able to do is we want to be able to understand what information is going on in each of these charts. Because I'm pretty sure that when we get together our next class into our last topic, woohoo, multiple regression, we're going to see these same charts, only they're going to be larger. So if we understand these 3 basic charts, we should be in good shape for our next class. Okay, so this first step, or this first chart, tells us how good is the model, how good is months of tenure at predicting what someone's current salary is going to be. So right here, what we want to look at is this value here called R. So that's what's the most important thing from our first chart. So that R and our R square, so that's the other one. So in our case on our last class, because it was simple linear regression, we'll have a value for R, and we'll also have a value for R squared. Next time when we get together, I think we're only going to see a value for R squared. So we can see that our R squared value is 0.007. That means this is a truly lousy model. How do I know if it's a good model? The closer it is to 1, the better the model it is. We could tell it was going to be a lousy model just by looking at the picture, but now we have numerical confirmation that, yes, this is a terrible model. Again, why? Because when we look at this R squared value, it's very close to 0. That means that almost none of the variation in salary can be explained by how many months you've had tenure. Okay, the second chart, which in SPSS is labeled ANOVA, this is the chart that gives us the equation of our regression line. Okay, so here we have, sorry, usually I don't use this software, so I'm still trying to get oriented myself. Sorry, let me just check one more thing. Okay, so on this one, the ANOVA actually, let me back up. The ANOVA is actually where we test whether the relationship is significant. Now, this, our square value being so small, told us it's not significant. But we can also formally take a look at this. Here we have an F statistic and a p-value right here. And see how that p-value is not less than 0.05? So we're going to say the relationship between these 2 variables is not significant. In the chart that's labeled coefficients, this is the one that gives you the way of writing your regression equation. Now remember, you should only do this if something is significant and this one isn't. So we really shouldn't write the equation, but first, for the sake of understanding these charts, we'll go ahead and do that. The one that says constant, that's your intercept. And then this one is the slope. So I don't know if I can type on this screen or not. Probably not. So let me open a Word document. Just a sec. Okay. So let me try to make it so you can see it. So what I'm doing is I'm looking right here at these two numbers. See that right here on this chart that's labeled coefficient? So if I were going to write the equation, I would write y is equal to, the constant is your y-intercept. So if you're thinking of y equals mx plus b from algebra, then I'm going to write y is equal to, the constant is b, and this other one is the slope. So I'm going to write 142.7x plus, and the b is 22643.3. And that would be the linear equation, the linear regression equation. And again, we know that we can write the equation. However, we also know that this relationship is not significant. So even though we can write the equation, we really shouldn't, because it doesn't give us any information about the relationship, because there is no relationship between the variables. Okay, I'm not sure how clear that was. Oops, sorry. But that's just kind of going over these charts. And we can definitely do some more of it in person, but I was just trying to give you a little bit of a flavor for what these charts give us. So the first chart we look at, the important number is r squared. When r squared is small, there's no relationship, meaning we really shouldn't go on and do any of this other stuff, but we're going to anyway. The second chart tells us if the relationship between the variables is significant. They run an f-test. Here we have our test statistic, here we have our p-value. The p-value again tells us there is no relationship between these variables. This third chart allows you to write an equation. If you think about y equals mx plus b, the first number is b, the intercept. We can know that because that's what constant stands for, intercept. And the second one is the slope. So that's why when I wrote the equation of the line, I wrote y is equal to this number times x plus this number here, the constant. Down here, we have two more charts which tell us we should not be doing this problem. This one here, because it's not a normal curve, it's skewed, we really shouldn't do this problem. And this is a normal probability plot, and because it's very wavy, it's not a gentle slope, it's quite a severe slope here. This also tells us we violated the assumptions of a normal distribution. But in any event, this was one of the examples in class, so I thought I would try to explain the three tables. I suspect that on the final exam, if Sheldon is saying he's not going to hopefully have us do any calculations, but will only give us printout, what I would expect would be a printout like this, and he would ask us something like, analyze this printout that came from a linear regression. Tell me what you know about it. And what we would say is, because we're looking here at r squared, and r squared is close to 0, there's no relationship. Our ANOVA chart tells us about the strength of the linear relationship, and again, there's no relationship. And the third chart helps us write a regression equation, which we should only do if there is a relationship, but just to practice, the first number is b, and the second number is slope. I'm going to make one last video this week which tries to explain why anyone would be interested in multiple regression, and hopefully that will help not only understand last week, but also understand the lecture that's going to come up next time. Okay, all for now.